Imagine a computer, not the one on your desk, not the familiar machine that you use every day for work, browsing, or gaming. Imagine one that uses the laws of the quantum world, a world that operates on principles vastly different from the classical physics we know, the world of atoms and photons. This is quantum computing. It's a realm where particles can exist in multiple states at once and can be entangled over vast distances. It's a new way of processing information, a way that leverages the peculiar and powerful properties of quantum mechanics, a way that could change everything. Classical computers use bits, zeros and ones. Quantum computers use qubits. Qubits are strange. They don't just represent a 0 or a 1, they can be 0, 1, or both at the same time. This is called superposition. It's a fundamental concept that allows quantum computers to process a vast amount of information simultaneously. It's like a coin spinning in the air. While it's spinning, it represents both heads and tails. Not heads, not tails, but both at once. This duality is what gives quantum computers their incredible potential. Another key idea is entanglement. This is where two particles become linked, and the state of one instantly influences the state of the other. Two entangled qubits are linked. This connection remains even if they are separated by vast distances. Measure one, and you instantly know the state of the other. This phenomenon puzzled even Einstein, who called it spooky action at a distance. No matter how far apart they are, this property can be harnessed to create incredibly fast and secure communication systems. Imagine two coins flipping together, always landing on the same side no matter how far apart they are. Always landing on the same side. That's entanglement. Spooky, right? This interconnectedness is what makes quantum computing so powerful. These quantum properties, superposition and entanglement, are the secrets. They are the keys to unlocking the immense computational power of quantum computers. They give quantum computers their power. Power that could solve problems that are currently unsolvable with classical computers. These computers are still in their early stages. Researchers are working tirelessly to overcome the technical challenges and make them practical for everyday use. But they hold immense promise. The potential applications of quantum computing are vast and varied. They could revolutionize medicine, materials science, and artificial intelligence. Imagine being able to simulate complex molecular structures to discover new drugs or materials, just to name a few. The impact of quantum computing could extend to cryptography, financial modeling, climate forecasting, and beyond. The future of computing is quantum, and it's closer than we think. Algorithms are like recipes. They're sets of instructions. They tell computers how to solve problems. Classical algorithms are designed for classical computers. Quantum algorithms are different. They're designed to harness the power of qubits. These algorithms take advantage of superposition and entanglement. They explore many possibilities simultaneously. This allows them to solve certain problems much faster than classical algorithms. Think of searching a maze. A classical computer tries each path one by one. A quantum computer explores all paths at the same time. It's like having a million computers working together. Quantum algorithms are not just faster, they can solve problems that are impossible for classical computers. Problems like breaking the encryption that protects our online data, or simulating complex molecules to design new drugs. Let's talk about Shor's algorithm. This groundbreaking algorithm, developed by mathematician Shor in 1994, has the potential to revolutionize the field of cryptography and beyond. This is a big one. Shor's algorithm is not just a theoretical concept, it's a practical tool that could change the way we think about security and computation. It can factor large numbers exponentially faster than any known classical algorithm. Why does this matter? Well, the difficulty of factoring large numbers is the foundation of many encryption methods we use today, because factoring large numbers is the key to breaking many encryption methods. Imagine a lock, a very complex lock. This lock is what keeps your sensitive information safe from prying eyes, the kind that protects your online banking information, your personal emails, and even your private messages. All of these are secured by encryption methods that rely on the difficulty of factoring large numbers. Shor's algorithm is like a master key. It can unlock these complex locks with unprecedented speed and efficiency. It can open that lock in a fraction of the time it would take a classical computer. This speed is not just a minor improvement, it's a game changer. This has huge implications for cybersecurity. If quantum computers become powerful enough, they could render current encryption methods obsolete, exposing sensitive data to potential breaches. If we build large-scale quantum computers, they could break the codes we rely on today. This is why there's a global race to develop quantum-resistant encryption methods. Governments and organizations are already working on new encryption methods. These methods aim to be secure against the capabilities of quantum computers, ensuring that our data remains protected in the future. Methods that are resistant to quantum attacks. These new encryption techniques are designed to withstand the computational power of quantum algorithms like Shor's. But Shor's algorithm isn't just about breaking codes. Its implications extend far beyond cryptography. It has applications in cryptography, material science, and drug discovery. For instance, in material science, it can help in simulating molecular structures more efficiently, leading to the development of new materials. It's a powerful tool that could reshape our world. From creating more secure communication channels to advancing scientific research, the potential applications of Shor's algorithm are vast and varied. As we continue to explore the capabilities of quantum computing, Shor's algorithm stands out as a beacon of what's possible. It challenges us to rethink our approach to security, computation, and problem-solving in the quantum age. The future of technology is quantum, and Shor's algorithm is a key part of that future. As we unlock its potential, we move closer to a world where the impossible becomes possible. Section 4. Grover's algorithm. Finding a needle in a haystack. Now let's talk about Grover's algorithm. This is one of the most fascinating algorithms in the realm of quantum computing. This algorithm is all about search. Specifically, it's designed to search through unsorted data. Imagine looking for a specific grain of sand on a beach. The task seems almost impossible, right? That's what Grover's algorithm does. It helps you find that one grain of sand efficiently. It finds the solution to a problem among a massive number of possibilities. Think of it as searching for a single book in a vast library. Classical computers have to search through each possibility one by one. This can be extremely time-consuming. Grover's algorithm takes advantage of superposition. Superposition allows quantum bits, or qubits, to be in multiple states at once. It searches all possibilities at the same time. This parallelism is what gives quantum computers their edge. This makes it much faster for certain types of problems. Instead of taking years, it can take just seconds. Think of a database search. With Grover's algorithm, you can find the information you need much quicker, or finding the optimal solution to a complex equation. It's like having a supercharged calculator. Grover's algorithm can speed up these tasks significantly. This acceleration is crucial in many fields. This has implications for fields like drug discovery, finance, and artificial intelligence. Imagine finding a new drug in a fraction of the time. Grover's algorithm is not as groundbreaking as Shor's algorithm, which can factor large numbers exponentially faster. But it's still a powerful tool. It's like having a specialized tool in your toolbox that makes certain tasks much easier. It highlights the potential of quantum computers to revolutionize many fields. From healthcare to finance, the possibilities are endless. As we continue to develop and refine these algorithms, the future looks incredibly promising. Quantum computing is set to change the world as we know it. So, while finding a needle in a haystack might seem daunting, with Grover's algorithm, it becomes a task that's not only possible but efficient. The future of search is here, and it's quantum. Section 5. Quantum advantage. Why it matters. Why are we so excited about quantum computers? Because they offer a quantum advantage. They can solve certain problems much faster than classical computers. Problems that are practically impossible for classical computers to solve. This advantage comes from the unique properties of qubits, superposition, and entanglement. These properties allow quantum algorithms to explore many possibilities at once. This is something classical computers can't do. The quantum advantage has the potential to revolutionize many fields: medicine, materials, science, artificial intelligence, and more. It could lead to new discoveries and innovations that are impossible today. Section 6. The future of quantum algorithms. We are still in the early days of quantum computing, but the future is bright. Researchers are working on developing new quantum algorithms. Algorithms that can solve even more complex problems. Imagine algorithms that can design new materials from scratch. Algorithms that can simulate the human brain. Algorithms that can break the codes of the future. The possibilities are endless. The development of quantum algorithms is a challenging field. It requires a deep understanding of both quantum mechanics and computer science. But the rewards are immense. The future of quantum computing is full of potential. And quantum algorithms will play a key role in unlocking that potential. They will shape the world of tomorrow in ways we can only imagine today.